Okay, our second example of a tree diagram. Here is problem number 76, in which we see right here we have the probability, we have a 10,000 switches, and the probability of getting a bad switch is 1,000, so 10%, and the probability of, we want to find out what is the probability of getting 2 bad switches. Okay, so here the probability of a bad switch. And as we look at this, my first thought when I did this, my voice is changing. Okay, the first thing I wanted to do was change this to 10%. Okay, which is really bad. Don't want to go with that company. Okay, but as we go on, we're going to find out maybe we shouldn't, but let's just keep going with it. Okay, the probability of a good switch is obviously 9,000. Okay, so, and that's 90%. So as I draw my tree, and here, as I entitled this switches, and it's either a good switch or a bad switch. Now, I'm going to use the fraction, and you'll see why in a minute. Because at first I didn't do it, and I'm like, it's easier to see with the fraction. The probability of the bad switch is 1,000 over 10,000, which means the probability of the good switch is 9,000 over 10,000. Now, just like with the egg situation, once we've cracked one egg, we have one less egg, right? Okay. So here, as this branches out, this is the switch number 1. So let's color code this. Here, this is my first switch. And here, this is first switch. And now these branches right here are going to represent my second switch. But again, let's put this in perspective. I've got 1,000 switches. And let's look at the good one. I have 9,000, I've got 10,000 switches. I've got 9,000 that are good. And with the second one, I can still have a good or a bad. So here, I am going to make this one good, make that bad, extend this a tad. Now I have one less switch. So I no longer have 10,000 switches. I have 9,999 switches. One less switch. And since the first one was good, that means I have one less good switch. So now I've got 8,999. Again, this is why I did not use the percentage, because when I did this earlier, having 90%, subtracting 1 from 90%, it wasn't taking 1% away, it was taking one switch away. So what is 900 minus 1? It gives us that value right there. We have 10,000 switches. What is 10,000? Again, one less switch. Remember, they are dependent upon each other. Just like the Jolly Ranchers situation that I think I may have put on the video yesterday, because I did 2 videos. The first one I thought didn't work, but anyway, in which every year when I was able to do Jolly Ranchers before the the health thing in California, I would grab all my grapes. Actually, I grabbed all my apples. So, and if there were 100 apples by the time you guys got them, they're like, where are all the apples? In my belly. Okay, because you had less of a chance of finding the greens. Now, it's not like I sat there and I took out all of, didn't spread them out, but what I did do was, oh, I want one, oh, here's a green. Another day, oh, I want one, there's a green. Okay, so the chances of you finding a green was decreased because you had less greens, and the chances of it happening was decreased also. Now here, let's look at the idea of bad. We still have one less circuit or one less switch, but that first one was good. So that means the bad ones are still available, right? So here, that is 9,000. Now we'll do the math on these in a few. More concerned about the logic behind it. Now let's look at the idea of bad. We have here one less switch. The first one was bad. Now we have 9,999 switches left. 9,999 switches left in the bag. The first one was bad, and these I'm going to refer to as the good ones. And here, the bad ones. And if your thoughts are, well, Ms. Yarbrough, you changed the way you wrote them. I did that for a reason, that it doesn't matter where the probability goes or where the words go. Okay? So, saying it again, the first one was bad. And the second one, that means I still have the same amount of good ones in there. So, remember there were 9,000 good ones. So that's 9,000 that goes right here. Okay. Okay, so yes. Because there were only 1,000. There we go. Okay, I understand. Okay. I thought you were saying here. Okay. But we're okay with right here. Okay. Now, let's look at the bad. So again, I've got 9,999. And now, the first one was bad. And now I'm saying the second one was bad. So I have 999 that are left. Okay? My math looking okay? Okay, now, what I want you to do is take the time to do your multiplication. But before we do our multiplication, I want to show you something that I showed you yesterday, what all this means. So first of all, here I'm going to be using G for good. So this right here, when these two things are multiplied, once you find that hot mess out, whatever it is, that times that. This is the product of the probability, of the good times the probability of the good given that you chose a good. Because please remember right here, based on the information, I said to you last night that this second branch was dependent upon the first. This happened with the understanding that this first one happened. I mentioned the idea that the probability of you going to this specific college is dependent upon your SAT scores. The probability of you going to that specific college is dependent upon your grade point average. As you do that math, please also remember that this is the same thing as saying the probability of a good one and a good one. And why does that look different or sound different than it was before? Because these things are dependent. Now the second example we do is going to be a lot nicer than this one. But let's push through these messes, or this mess of all these funky decimals. So go ahead and do the math, guys. Now, this is my logic. Just like as we were making up this tree, if there are 10,000 that are bad, 1,000 that are bad, out of the 10,000, and then that gives us one less out of the total, looking at the denominator, and then one less defective looking at the numerator, I would just figure this out, do it this way, with this being switch 1 and that being switch 2. And we know, based on the idea of dependent probability from prior classes, I'm just going to be multiplying switch 1 times the probability of switch 1 occurring times the probability of switch 2, and then I'm going to get my math. That's bad. Okay, also look at this right here. Wouldn't I just multiply that times that to get that? And if I use this tree, how is that working? Here's your bad times your bad, which gives you that. All this other stuff, which yes, you have already found the answers to, okay? It doesn't matter because it does not help me answer my question, because my question says 2 of them bad. There's the first one bad. Here's the second one that's bad. I did the math to find out the answer. You're going to need more room for this simply because this, ladies and gentlemen, is going to give me 3 branches. Because I need one for white, I need one for black, and I need one for Hispanic. Okay? So my point is that give yourself some room. You might have to put this on another sheet of paper. Okay, now. Okay. Here are the voters. And we have the black, the white, the Hispanic. They said that the city has 40% white, 40% black, and 20% Hispanic. But then you've got this mayoral candidate. And with that mayoral candidate, here they either support him or they don't. Okay, so here I'm using S for support. And of course, somewhere you need to have written down B for black, W for white, and H for Hispanic. But just like I have S for support, I'm going to also have S not for not support. And then I am going to put in right here support, not support. And I'm going to do that for all of my branches. Okay, now please notice that the length of the branch is not relevant. Okay, so here, as I look at it, it says that we have that 30% of the whites want to vote for him, right? Okay, so 30% support him, which means 70% don't.
That's the black's branch.
Oh, touche. Where are my whites?
In the middle.
There you go. Okay, here's 30%, and here is your 70. Okay, let me get rid of this. Okay, so blacks, 90% support him, and 10% don't. And then here, I have, and I'm going to move this in a minute. Should have kept this on the outside. Here, for the Hispanics, I have my 50-50, right? And just like we did before, I am going to do the math. So go ahead and multiply. Okay, look up and check out your final answers so far. And this is all that I'm asking for of you now. Again, to build a tree, to build a tree. And just quickly talking to you about what I was showing you earlier with the good switch and good switch, which was really kind of hard to comprehend because everything was a G. Okay, let's see what this is saying right here. Here, please remember, and this is based on the stuff from last night, that's the probability of white times the probability of white, or times the probability of support, given that they were white. And that represents the same as the probability of white and supports him. And please, again, like I said earlier, if you're like, well, Miss Yarbrough, last time all we did was multiply, these situations are dependent. That's why, even though the equation looks the same, the results are different. Okay? Okay, so now we're about to do QR codes.